I'm going to talk about Greece from now, and we're going to use more InSAR data to have a look at some of the extension going on in Greece, looking at specifically how normal faults show different behaviors in these data sets when you look at the InSAR data over time series. So a bit of a combination of both of the things we've seen so far. So this is the first part of my PhD at Imperial in London with Rebecca Bell and Alex Whitaker here. So the start, I'll just talk about EGMS dataset. So this is InSAR time series dataset across Europe. And then I'll briefly touch on how we can use that to look at earthquakes, how coseismic signals are recorded in the data, and then move on to how aseismic fault motion is also recorded in the dataset. So this is essentially a summary of this study, which has been out for a couple of months now. So feel free to scan the QR code if you want to take a look at that and have a read. I will move on to the data itself. So if you're unfamiliar with this data set, I definitely recommend going to this web address here and taking a look. It's essentially an open source data set of Sentinel-1 time series data across pretty much all of Europe. I see there's a few gaps missing, but the key areas we're looking at here are Greece, and people have looked at Italy in the past. So if you go onto this browser, you can see areas like Mount Etna here. If I just do that, and you can draw a polygon and you can get out a time series, time on the x-axis here, displacement on the y-axis for all of these plots of how the ground is changing over this 5-year period. And each point here is 6 days based on the return period of the Sentinel satellites. So we have the line of sight data, but the stuff we're going to be using here is the decomposed vertical component of this ground motion. It's just more simple to work with. So people have started to think about how we can use this data in tectonic settings. So this study last year by Zoe Milne et al. Looked at the data in the Gulf of Corinth on the Pericora Peninsula to show that there's this differential ground motion across the Pisia Fault without any associated seismicity. And then people have started to think about the scale of this data set and how you can look across the whole countries and comparing. So this study by Cardello et al. Compares the InSAR up-down rates to high stand deposits of MAS5E and vertical GNSS component data. So if we take the data and for central Greece and look at it here on top of active faults in white, and all of these plots from now on, red colors represent subsidence and blue colors are uplift. There's a few things that we can pick out from a first order observation. The first one is this area up in the north near Larissa, where we have this big signal, which is definitely associated with the 2021 earthquakes that happened here that we'll take a look at in a minute. But then there's some more subtle signals as well in here. You'll notice that the vast majority of the area is sort of a red or a neutral color, but there's a few of these patches of blue uplifting land without big earthquakes associated with them or other anthropogenic and groundwater influence over these areas. So setting up this study, we wanted to try and record how all styles of fault behavior can be seen in this data set and how we can potentially use this moving forward to study fault processes in Europe. So if we then look at this earthquake sequence in Larissa, so this happened in 2021, there were 2 main shocks of greater than magnitude 6, and then a large aftershock a few days later. You can see in this diagram there's a bunch of aftershocks as well associated with this earthquake sequence. The faults that it happened on were previously unmapped before the earthquakes happened, and there's plenty of differences in opinions in the published work on the rupture planes, especially of this earthquake sequence. So lots to still think about with this earthquake. So from this, we wanted to use this open source time series data to, in the first instance, try and do the things that you'd maybe do with a normal traditional InSAR study with interferograms immediately after an event. Things like getting uplift and subsidence patterns, rupture plane projections, and amplitudes of ground motion, but also try and look at this in time as well and see how things have changed in the pre and post seismic and the sequence itself. So this now zooming in to the point data of this earthquake. We've split this area up into 3 time series blocks. So essentially the time series that you can see in this plot are just an average of all of the points, thousands of points in this instance, in these blocks. And very simply to start with, we wanted to convince ourselves that what we're seeing over the 5-year period is vastly dominated by the coseismic motion. And I think if you look at this plot with the earthquakes, the moment released by the earthquakes in orange and the number of aftershocks in blue, you can see that the ground motion associated with the earthquake is an order of magnitude, 2 orders of magnitude greater than any of the pre and post seismic. And there's 10 millimeters of post seismic relaxation in the red block as well, which is interesting, but I won't go into too much now. But we can look at the sequencing of the earthquakes and try and get something out of this looking at this data from time series instead of just looking at the data spatially. If we take this blue block, for example, in the north, we can see, so it's actually hidden by the purple time series before this point, but it drops down over 1 6-day period, and then 6 days after that, it's gone up quite considerably. So a tectonic interpretation of that might be that it was in the hanging wall of one event in the first instance, and then has moved to the footwall of this normal fault earthquake after that. And you can see that the red block goes down in both events and then stabilizes. So we can start to think about the sequencing of where these ruptures happened, especially if we didn't know when they happened, where the precise location of the faults were. They've not got big topographic escarpments. And we can then put it into now extracting those key imaging periods, so those 6-day imaging periods, looking at this spatially. So instead of looking at the raw point data here, we've just essentially applied a contouring to this with the vertical motion. And we were quite lucky in this first image here that the second part of the interferogram was taken only a few hours after the earthquake happened. So it quite nicely isolates this first shock. And we can see in this that there's this big patch of uplift in the southwest and subsidence in the middle of this map. So it's quite straightforward to plot a rupture plane on there. This second part of this figure shows the next 6-day period, the largest earthquake in that period being the magnitude 6 on the 4th of March. And we can see now that the main uplift has shifted over to the north of the subsidence patch. So for us, we were happy to infer a rupture plane to the north of the subsidence, a southwest dipping structure, so an antithetic structure to the main shock. We can also do things like putting this into profiles. You can see a nice bell curve produced by the uplift pattern of this red profile. And we can see some of the complexities, excuse me, in the subsidence associated with this blue profile in the center here. This step profile is quite interesting. Again, we can do profiles across strike. We can infer rupture planes perhaps in here. We can think about things like the uplift to subsidence ratio using this data set. And it's all already processed. You just have to extract the part of the time series that you want to look at. So that was quite successful for us. But then moving on to where signals are less obvious is really where we see the value in having this time series data. So we're going to look in the North Gulf of Evia now. So if you're familiar with the Gulf of Corinth, that's the fastest extending rift in Europe. The Gulf of Evia is a similar setting with 1 to 3 millimeters a year of north-south extension. And we're going to look at this Kamenivola fault, coastal faults. It's a pretty well mapped fault system. This is the footwall topography of it here. This is the town of Kamenivola. So it's quite obvious where the fault scarps and the footwall and hanging wall of this fault are. So we're not having to do any mapping ourselves with this InSAR data. And it doesn't have any historically attributed major historical seismicity. So our aim, looking at an area like this, is to investigate where we have this ground motion in a non-coseismic setting and how that interacts with the normal faults of the region. So we've zoomed in quite a bit now, so a much finer scale. And also the color stretch on this is a lot finer as well. So the maximum saturation of these points is only 2 millimeters in uplift and subsidence. So this western part of the figure is the Comenifola fault. You can see it's quite a nice normal fault. It's quite obvious in the topography. And you can, from where the plane is mapped, you can clearly see that we transition from uplift in the footwall to subsidence on the planes down here. Interestingly about this fault, the fault is mapped along the foot of the escarpment here, but actually we have some uplift in the town as well, which is traditionally mapped in the hanging wall. So we've had to infer an offshore splay of the fault here. If we quickly look at that now in time series, we're showing this footwall block then in blue here, and the hanging wall, the subsiding hanging wall in yellow. You can see that everything here is happening quite consistently. The footwall is uplifting at a velocity of 1 millimeter a year, and the hanging wall subsiding at 2 millimeters a year. So in terms of the geological throw happening on this over a 5-year period, it's happening at 3 millimeters a year, which is pretty significant in terms of rates for this region. And comparing that to the earthquakes again of the area, these are all small to medium sized earthquakes, magnitude 3s and 4s. But we can see that on the time series, they don't really have too much of an impact on either the small wiggles, maybe there's a little wiggle associated with this earthquake, or the overall trend of what's going on in this area.
You're now at 11 minutes.
Great, thanks. Of course, groundwater can play a role in these time series quite significantly, but we're quite happy with this signal in the footwall, given that it's pretty well liquefied limestones and other sediments. And if we were to consider the hanging wall to be quite impacted by groundwater, we could apply a ratio of 1 to 2 uplift to subsidence, as you'd expect for faults in this area, and get a similar result from the hanging wall as well. So in terms of the rate of that happening at 3 millimeters a year in this region where we're only expecting extension of 1 to 3 millimeters a year, it's obviously perhaps too high for what we might expect, given that there's other faults as well in this rift that are accommodating strain. But also in terms of longer term geological rates of 100,000 to a million year rates on this fault, people have resolved that to always be less than 1 millimeter a year of footwall uplift. But we're actually seeing from this signal that we're getting 1 millimeter a year of footwall uplift without any earthquakes. So it would perhaps be a bit wild to say that we're producing all of our footwall topography aseismically, but if we just extrapolate this signal, that would produce that. So we think this isn't a behavior that's happening all the time. It's time-bound, has to be a time-bound thing at rates this fast. So it's something akin to a slow slip event on this Comenifola fault. So just putting those two things into a framework, and thinking about the implications of it on the earthquake cycle and seismic hazard in this region. If we're taking a rate, geologically derived uplift rate, for example, from either fluvial terraces, drainage analysis, you may then extrapolate how many earthquakes you need, how long is the recurrence interval may be to produce this footwall uplift. Well, in reality, maybe you're able to accommodate some of that uplift with this aseismic notion, either a creep behavior or a slow slip type event. And maybe you're then ending up overestimating how big your earthquakes need to be, how many earthquakes you may need to generate that topography. So that is all from me. Just to conclude, this data set is amazing. You should just definitely go and have a look at it and play around with it, especially if you work in Europe. It's providing a simple approach to observe vertical motion, not just fault motion, but so many other geological processes at high resolution over annual to decadal timescales. We can see coseismic slip quite nicely in the data set. We can see aseismic slip as well on some normal faults. We've got this 5-year period of elevated aseismic slip on the Comenifola fault that we interpret as something akin to a slow slip event. And perhaps thinking about this variable behavior on faults needs to go into some more thinking about seismic hazard on these major active structures. And there's so much potential with this data set for active tectonic studies that, yeah, everyone should play around with it for sure. That's all.
Thank you, James. That was great. A very, very rich data set to play with. I have a question. If anybody has any questions, please put them in the chat or put your hand up. In the interim, I have a question about the Larissa earthquake from, I don't know, 6-ish slides, perhaps more back. With respect to
This
those
one?
yeah, that one.
Sure.
So on the vertical displacement plots, the blue curve, is that showing that there's like partitioning across two faults, or is it maybe because the cross section isn't clipping it at right, like along the fault plane? What do you think?
Yeah, this always comes up whenever I show this plot. It's a bit weird. There's possibly some partitioning going on with the structure in here, but also because it's a 6-day period, there's quite a few sort of low magnitude 5, 4 earthquakes happening in here as well. So maybe there's something happening with the aftershocks there's more aftershocks affecting this portion of the subsidence, or it's disturbed us. But whether there's a geological reason or not, I'm not sure. This uplift component is really nice. Maybe it is just that we've drawn the cross section in slightly the wrong place to get a better representation of that subsidence, or maybe it's a genuine structural oddity that's caused this this funny stepped profile.
I wonder if you could somehow like just make a non straight line, but just kind of like run
Yeah.
through the max and see if you still get that double like camel kind of thing, inverted camel.
Yeah,
Um,
possibly. I think we would. I think this across all of this area, it's less. The amplitude of the substance is less than over here.
Regardless.
Uh,
Okay.
yeah. So people have spoken about this Misakori fault as being potentially an important in the aftershock sequence. So possibly there's some partitioning of the substance happening there. But yes, not we don't fully understand why this signal is there. But it's certainly quite interesting.